Welcome back. In the last lecture, we were discussing some very basic issues. We were debating whether program writing is a art or a engineering. We said that initially every technology starts in an art form, slowly becomes a craft and then graduates into an engineering approach. Software is no different, and in the engineering approach we said that the past experience of large number of program developers has been systematically investigated, documented, scientific basis techniques have been provided, but then some are thumb rules. We will look at those thumb rules as we proceed and the techniques. Now, let us continue with what we are discussing. Let us try to understand what is exploratory software development. Exploratory software development is the software development practice of a novice. Let us say somebody who is just starting to program, just learning programming and is doing small assignments. How will he develop the program? That we call as the exploratory software development or the build and fix style of development. This is the same style which the early programmers used, because there were no other techniques. They had to use their intuition and develop, and that is called as the build and fix style. In this style, as soon as a problem statement is given, based on the understanding of the problem statement, start writing the program. And normally that is a dirty program, in the sense that it will have lot of bugs, and then the programmer tests it, the bugs are fixed as and when they are noticed. If we document this development style, the build and fix style, in the form of a schematic diagram, we will come up with this diagram. As soon as the problem is given, we document, we do the initial coding, and after the initial coding is complete, start testing, find that there are large number of bugs getting reported. Maybe some of them are crash, the program crashes, or maybe just large number of bugs, compilation errors and so on, and then just fix it. Again compile, test, and again see that there are errors, keep on this cycle, fixing the program and testing, keep on doing it until you find that okay, it is as per your understanding of the requirement for the program. So, this is the model of a exploratory style of development. Let us keep this in mind, because as we proceed, we will once in a while contrast with this basic style of development with the engineering style of development. But one thing is that if we use the exploratory style, as most of the new programmers use, they can develop small programs. But then if the project is non-trivial, it is a large project requiring hundreds of thousands lines of code, and you do this, that initial coding, find errors, keep on fixing, this will not work, the project will never complete. And even if somebody really puts lots and lots of effort, completes it somehow, you will come up with a very poor quality of software. But then what is the basic reason? Let us try to investigate that why is it that this style of development, the exploratory style is does not work for large projects, only for very trivial programs we can use the exploratory style. Let us try to understand that what is wrong with the exploratory style. To understand this, let us look at this plot. As the program's size increases, you develop large and larger programs and still keep using the exploratory style or the build and fix style. You will see that for small programs, okay, maybe you are successful, but as the program size increases, the effort, time, cost all increase exponentially. Maybe to develop, let us say, a 100-line program you just took couple of hours, but to develop a 1000-line program you took several months. But then after some size, the exploratory style just breaks down. Even if you try your best using the exploratory style, still you cannot develop after certain size. Whereas a software engineering approach, just let us look at here, there is almost a linear increase in the effort, time, cost compared to the program size. So, if a 1000-line program took couple of hours, a 10,000-line program should take only about 10 times of that, not like 1000 times or 100 times. But then let us assume that there exists a machine to which you can give the problem statement and it will come up with the code. It is a robotic machine which can write code. If that can be realized, then it will be exactly linear. If it takes some time, some cost is incurred, you give 10 times, exactly 10 times will be incurred, whereas using software engineering principle, it just increases slightly. We will see why. But then one very basic thing we need to remember from this slide is that the exploratory style, the cost, effort, time, they increase almost exponentially, whereas using software engineering principles, we are keeping them down to almost a linear increase. But then the question naturally arises is that why is it so? What is wrong with the exploratory style? Why is it that the exploratory style, the cost, effort, time to develop increase exponentially and also break down after certain size? And also the other symptoms are that the programs are poor quality, unmaintainable, and it is very difficult to use the exploratory style in the team development environment. But let us investigate why it is so. What is wrong with the exploratory style, whereas in using the software engineering principles we are able to overcome this. So, that is a basic question we must understand the answer to that. We should be able to answer that why is it that the exploratory style, there is exponential increase in the effort, time, cost, and we keep that down to a linear using software engineering principles. what is really the thing that is working here for software engineering. Let us investigate that, because that is a very fundamental principle why software engineering works, whereas the exploratory style does not. To understand that, we need to little bit understand the human cognitive mechanism. Long back result from Miller 1956 said that human memory can be thought of made of two distinct parts. One is a short term memory and the other is a long term memory. And as the name says, the short term memory is one where we remember something for only a small duration of time, maybe several seconds or just minutes, whereas long term memory remember it for months, years and so on. A short term memory, if it is there, we tend to forget it after some time. Let us see the working of the human cognition mechanism. Let us say, I just say that see, look at the watch, it is 10:10. How many hours remaining today? It is 10:10 by the watch. How many hours remaining today? The way the human mind will work is that 10 a.m. that is in the short term memory, you saw the time, it is 10 a.m. and from your long term memory you will fetch that one day is 24 hours, and now that is also in your short term memory, that 24 hours is a day, and then there will be a mental manipulation unit which will compute the difference 24 minus 10, and then you will say that okay, it is 14 hours or 13 hour 50 minutes. If we put that down in the form of a diagram, we will see that the long term memory holds large number of items. Depending on the person, it can hold billions, trillions of items, whereas a short term memory can hold only few items, and then these are fetched from the long term memory, the short term memory from the observation, looking at the clock and so on, 10 a.m. and then the processing center where some computation can be done and the answer is given. But then what exactly is the short term memory, what can it store, how long? Let us look at it. An item stored in a short term memory gets lost with time, maybe several seconds, minutes or hour. It gets lost from the short term memory because there are too many new information that has come into the short term memory, or that it just plain decays with time. But then the main thing is that it stays for very short time, and depending on whether there are many new information coming, the time duration can be even very short. It can be typically tens of seconds. But then somebody can remember something longer by recycling in memory. For example, you went to the market, wanted to buy some things, just keep on recollecting again and again that what you need to buy. So, recycling in the short term memory. But then we said that the short term memory stores items, but what exactly is an item? An item can be a character, it can be a digit, character like A, B, etc., digit like 5, 6, etc. It can be a word, a sentence, a story and even a picture. If somebody remembers some numbers, let us say 5, 9, 7, etc., each one is considered one item. But then if there is a relation between them, then it can be considered as a one item. Let us say 1 to 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, that will be one item, because you recognized that there is a relation, it is 1 to 9. Similarly, a word, individual letters, if there is no relation, there will be separate items, but if they are related, they are a word, mean something, then that is just one item. A sentence is one item, story is one item, and even a picture is one item, and they occupy one place in the short term memory. One conclusion here we can make is that if you are remembering something and you are able to build a relation between the things that you want to remember, then it becomes easier to remember. That is called as the chunking. Let us just look at as an example of chunking. Let us say I ask you to remember the number 1100 101 01 001. You will struggle to remember this, because there are too many digits, and then the relation among them is not so obvious. But then let us say just group these into 3 and I give you the octal form 6251, then it becomes easy for you to remember, because the short term memory about 7 items it can easily remember, and anything more than 7 there is a exponential increase in effort to remember. You will have to look at various relations between them, try to reduce. Let us say you might say that initially 2 or 1, then 2 zeros, 101, etc. You will struggle to find relations, reduce it, chunks, and then try to remember. So, that becomes very hard to remember a large set of items. That is because of the limitation of the human cognition mechanism, that the short term memory can hold only 7 items. And as long as you are able to find relations and so on, it becomes easy for remembering that, as long as it is less than 7. So, that is the principle of chunking. There are many day to day experience where you can, the short term memory is evident. For example, you looked up a number, telephone number, and then you found that you are not able to dial it, it is busy. But then you will see that after a few minutes you are almost able to remember the number. But what about after several days? You will hardly remember anything. But then the number of items that somebody can store in short term memory is about 7, and that is called as the magical number 7. Any set of information which has 7 items in it, for an ordinary person it becomes easy to understand that. But if the number of items are large, let us say tens of thousand, let us just look at an very trivial example. Let us say you met 5 people somewhere, you will almost remember them. But let us say you met 10,000 people for 10 minutes, hardly you will remember anybody. That is because of the number 7, that is the short term memory capability is restricted to 7. So, if the information has more than 7 items, it becomes exceedingly difficult to understand and to remember. If it has let us say 15 items, to understand and remember you take exponential time compared to if there are 5 items. If there are 100 items, then it becomes real difficult. But then you would ask that why what this has got to do with programming, and how does it provide an answer to the exploratory programming style, the effort, cost, time duration etcetera increasing exponentially, breaking down after some time, whereas software engineering is able to hold it linearly with respect to the problem size. The answer is that to understand a program, we must look at what are the variables, how do they interact. Let us say you are writing a small program having only a couple of variables. You can easily look through the code, understand what is happening. But let us say you are looking at a program which has thousands of variables there, and each variable is set by some programming constructs being used and so on. For the human mind, it becomes extremely difficult to understand that what is going on in the code, how does it work, what is it achieving and so on. So, as long as the number of independent variables in a program is small, it becomes easy to understand, but as the number of variables in the code increases, it becomes very difficult to grasp, to understand, and requires an unduly large effort to master the problem. But then the next question that arises is that if that is the case, that if the number of independent variables and so on are more than 7, it is a large problem dealing with many things, then how does the software engineering principles, they contain the complexity of this problem. Actually, before we answer that question, I will just like to mention that for machines there is no such problem as short term memory. Of course, they have RAM and so on, but then the restrictions are not so severe. So, if a machine would like write the code, then the slope would be almost linear. Now, let us understand how the software engineering principles contain the complexity, because we said that as the complexity increases, the human mind by itself would take exponential time, effort to understand, to solve the problem. Actually, there are two major techniques that are used to overcome the cognitive limitation of 7. These two important principles are used in almost every technique that we discuss in our lectures. One is called as abstraction and the other is called as decomposition. Let us understand what exactly is abstraction and what is decomposition. These are two independent techniques. How do these reduce the complexity of a problem? And then later, when we use these techniques in various software engineering tools and techniques, it will become clear to us that whether we are using abstraction or decomposition. Now, let us investigate these two fundamental techniques to handle complexity, because software engineering is after all developing programs efficiently. As the size increases, we want to develop only with linear time, cost, effort and so on, and for that we need to effectively handle complexity, increase in complexity, and these two techniques to handle complexity are used in almost every software engineering principle. Let us look at these two techniques. One is the abstraction. Let us see what is meant by abstraction. In abstraction, we focus our attention only on some aspect of the problem and ignore the rest. This is also called as model building. Let us say we want to develop a large building. Now, we want to see that how does it look like. We will ignore all other aspects like what are the strength, what is the wall thickness, what is the internal plan and so on. We just want to see how it will appear. Then we will concentrate only on its frontal appearance and we will ignore everything, and we can construct a model of that, the frontal view of the building. Similarly, we can let us say we want to see what will be the floor plan for a building. We will just concentrate on that. We will not bother about how does it appear externally, the thickness of the wall and so on. We are just concerned about the floor plan. If we are, let us say, concentrating on let us say what is the heating requirement of a room, we will just look at how much is the where is it located, is it in the top floor, how much heat it is getting, etc., and we will omit other unimportant aspects. For every problem we can construct an abstraction. The abstraction is also called as a model building. If we create a model, we concentrate on some aspect and ignore the rest. So, model building is the same as an abstraction, and this is an important technique in software engineering for we want to build models of everything, requirements, design, code, etc., and that is one way to tackle complexity. We will stop here and we will continue in the next lecture with this abstraction, decomposition and so on, and we will look at the other issues in software engineering. Thank you.